Oh, look at me. I'm teaching. All right. Hi, guys. How you doing? So as you can see, I'm not in the classroom. I'm here in the gym because we're doing yet another performance of She Wrote, She Died, and then She Wrote Some More. Um, oh, the Wi-Fi is buffering. I wonder if that's coming through okay. Uh, well, we're going to hope for the best. And if this is a nightmare, whatever. The last check can teach it. So yesterday we started looking at chemical equilibria. And when we talked about equilibria, what we meant was situations where a reaction can run in two directions. There's a reaction that can happen, but then its opposite can also happen. So, a reaction where you put two things together and they can form a product, but then those two products can react and actually give you back what you started with. And if both of those reactions can happen and are possible, period 2, please. She's got my period 1. I need to know who has my period 2. If both those reactions are possible, then this will happen. We get what's called a state of chemical equilibrium. And in a state of chemical equilibrium, eventually, at some point, the forward reaction and the reverse reaction will happen at the same rate, and we'll end up with what we call a steady state. We'll end up with a situation where the concentrations of everything are fixed in place. So let's take a quick look at yesterday's note, just sort of as a reminder of what that looked like, right? We said that as we have the reaction A forming B, we also have the reaction B forming A. And you know what? I might just give you just a little piece of me here. Because I think maybe my hideous face explaining this might actually be useful. All right, there we go. So, oh God. Okay, so, so as the reaction happens, A gets used up, its concentration goes down, but B gets made, its concentration goes up. And the problem is we know that the rate of the forward reaction depends on how much A we have. So as it's getting used up, that reaction is going to be slowing down. The rate of the second reaction that uses B depends on how much B we have. So as it gets made, it's going to speed up. But then at some point, because B is getting made, A is going to speed up again. But then that will mean that at that same time, we get a decrease in this, and they go back and forth, and eventually we reach a steady state, and we call that steady state equilibrium. Now, the concentrations could be anything. You could have a ton of A and only a little bit of B. That could still be a steady state. That could be equilibrium. You could have a ton of B and not much A, and that could be a steady state. The fact that they equal the same speed doesn't mean they have the same concentration. You'll note that these aren't coming in at the same concentration. They're just leveling out, which means that they're not being used up or made any faster than one another. So the fact that they reach equilibrium does not mean, and this is a key point, it doesn't mean that the concentrations end up equal. They don't. In fact, how they end up is going to depend on how fast those reactions are. It's going to depend on the rate. So we showed that if you wrote a rate law for each of these, at equilibrium they'd be equal to each other. And then we said, well, you could solve for this by combining the two rate constants, K, together, putting them on one side, and putting the concentrations on the other. And in that case, we can make a new constant called the equilibrium constant that depends on the rates of the reactions, but itself doesn't say anything about the rates. Rather, it says something about the concentrations. And we call this a rate law, an equilibrium law, or an equilibrium constant, or an equilibrium expression. And those are all synonyms for the same thing. It's this equation here where we say that for every reaction that exists as a state of equilibrium, if you multiply the concentrations of the reactants by each other and divide it by the product of the concentrations of the reactants, you'll get a constant value. And I just said reactants twice. The products go on the top and the reactants go on the bottom. And whatever the coefficients are in front, those will become exponents in this. And we went through yesterday why that's true for equilibria, but not true for rates. That may or may not be clear to you now, but I don't want you to worry about it. I do want to make a note. Don't go back in time and start always just using the coefficients when you do rate expressions. They're different for a reason. But for equilibrium, it's actually much easier than doing rate laws. Rate laws, you have to figure out the exponents. Equilibrium expressions, you take the coefficient, that is the exponent. Concentrations of the products on the top, concentrations of the reactants on the bottom, the exponents are all their coefficients. And that leaves us with this here. So for example, if we had ethine reacting with oxygen to form carbon dioxide and water, the concentration of carbon dioxide to the power of 4 times the concentration of water to the power of 2 divided by the concentration of ethine to the power of 2 times the concentration of oxygen to the power of 5 is going to be a constant. We call that the equilibrium constant. And that equilibrium constant will remain constant as long as your temperature and your pressure don't change, right? And so we had to do a second example, this time with actual numbers, and we could actually sort out the constant. We could solve for KEQ, which we did here. That KEQ value can then be used to predict what will happen when we change the equilibrium. And that's the real point. The real point of equilibrium isn't just that it reaches a steady state, though it does. The real point of doing this then is that we can manipulate equations by changing conditions to drive the equilibrium in the direction that we want. So if we have a desired product that we want to make more of, if we have a reaction that comes to equilibrium, we might not get that much of that product. And so what we can do is say, well, how could we change conditions so that that product is favored? And this introduces us to the idea of Le Chatelier's principle. The basic idea of Le Chatelier's principle is, like I said, if you've got a small kid in your life, you understand Le Chatelier's principle, which is that any change you introduce into the chemical system, the equilibrium will naturally work in opposition to that. So, yeah, they can come get them, do so quietly, please. I just got to finish recording this. In fact, if you want to start moving those maybe to over there, that'd be great. So, let's look at what that means in practice. Well, we said if we have a reaction, such that A plus B yields C plus D, if we increased the concentration of A, well, that would mean that now the forward reaction is going to go faster at first. And if the forward reaction goes faster at first, then what's going to happen is we're going to make more C and we're going to make more D, and we're going to actually lose some A and lose some B. So if we increase the concentration of A, when we get to a new equilibrium, the concentration of A will have gone down. But because the concentration of A went down, the only way the concentration of A can go down is if the concentration of B also goes down. But the concentration of C is going to go up because it's getting made as A gets used up, and the concentration of D is going to go up. Now, that would also be true if we increase the concentration of B. Right? On the other hand, if we increase the concentration of C, or if we increase the concentration of D, now, again, the reaction is going to start happening. Increasing C or D means that the backwards reaction will be favored. It'll happen faster. And when that happens, a new equilibrium will eventually happen because these things will eventually sort speeds out again. And in that new equilibrium, the concentration of C will have actually dropped compared to when we added the C. The concentration of D will have dropped with it. Meanwhile, the concentrations of A and the concentrations of B will have gone up. Not only concentrations going up, what if we could remove this? What if there was some way to remove D? Well, if we did that, that would mean that the concentration of D would go down. And so then you would get the equilibrium would be broken, and it would change around for a while, but eventually we'd come to a new equilibrium. And in that new equilibrium, if the concentration of D dropped, that means the reverse reaction slowed down, which means for a little while, the forward reaction was faster. And if the forward reaction was faster, that means the concentration of C would have gone up, the concentration of D would have gone up, and the concentration of A would have gone down, and the concentration of B would have gone down. All of which is to say, if you want to move an equilibrium, you can just add more of something or take something away, and the equilibrium will shift to compensate. If you add more D, the equilibrium is going to shift to get rid of it. If you take away D, the equilibrium is going to shift to replace it. If you add more A, the equilibrium will shift to use up that A. If you take A away, the equilibrium will shift to make more of it. So whatever you do, the equilibrium system is going to undo. Now that makes perfect sense for a reaction like this, but we don't just have to necessarily change concentrations. Even though that's what's in the equation, there's other things to think about. Changes in pressure. So for example, if we had water in its gaseous state decomposing into hydrogen and oxygen, which is a reaction we've seen a lot of. And to balance that requires 2's there. And these are all gases. If we changed pressure, that will affect this system. You might ask why. Well, the answer is, over here, we only have 2 moles of gas. In other words, N equals 2. Over here, on the other hand, on the product side, we have 3 moles of gas, 2 moles of hydrogen, 1 mole of oxygen. N equals 3. And of course, you know that for both of these, PV equals nRT. And over here, PV equals nRT. Now, if we add pressure, if we increase the pressure, the system will want to lower the pressure. Right? That's what Le Chatelier's principle tells us, is that if we introduce a change, the system will want to undo it. Now the problem is, we would increase pressure mechanically by pushing down on a piston or by squeezing on the side of it or something of that nature. But the reaction can't do that, assuming we don't let it. Obviously, if we let it, the piston would just shoot back up. But if you hold that piston down so the pressure is stuck, it can't do this directly. So it has to do this by the reaction. So now let's think about that. If it has to lower the pressure by the reaction, what can it do? Well, remember this is an equilibrium. And because it's an equilibrium, it can shift in either direction. And if PV equals nRT, if N is lower, pressure is lower. So it can do this by a reaction, and how it can do that is by lowering N. And the way it lowers N is it would shift to the left. And by shifting to the left, that means that it's going to make more water and less H2 and O2. And that is going to do that. On the other hand, if the pressure goes down, well, now we're going to get a new equilibrium that it's going to try to raise the pressure back up. So if you had this reaction happening in a piston and you reduce the pressure of that system, the reaction is going to try to counteract that. And the way it's going to do that is by making more pressure, which means it needs to raise N. And it does that by shifting to the right. When we say shifting, when we talk about an equilibrium shifting, we just mean that if it shifts to the right, it means for a little while it makes more of the stuff on the right. And when it comes to a new equilibrium, we have more of this stuff than we did before and less of the stuff on the left. When we say that it shifted to the left, it means that it makes more of this stuff and we've used up more of that, so we have less of it. So in pressure, in a gas state, it's going to counteract by lowering how many moles we have. And you can just count how many moles of gas. Because one of the things we find in PV equals nRT is that pressure doesn't depend on how big the molecules are or whatever, just how much gas you have. More gas, more pressure. Less moles of gas, less pressure. So Le Chatelier's principle tells us that changes in pressure there. So what about temperature changes? Temperature changes. Well, if we had a reaction like, say